So I guess the key point I want to make is what we can do when we've got sub-arc-second localizations of FRBs and high time resolution observations of FRBs, and what we can do to combine those two observational data sets to inform us about how FRBs are produced and how we can use them to study intervening space. So the project I'm talking about is CRAFT. The collaboration is largely Australian, but we benefit a lot from our work with Xavier Prochaska and his F⁴ team. And the goal of the project is to observe commensally with everything else that's going to be going on the telescope. So ASKAP is in Western Australia. We've got up to 6 kilometer baselines, and the antennas are equipped with these phased array feeds. So we get 36 beams. So we have a 36 camera pixel on the sky, 30 square degree field of view, and we can observe anywhere within this frequency range. It's not the world's most sensitive telescope, so what we're doing is we're really probing sort of the bright burst population. We have 2 data products, and this will become important later on. So when we search for data, we have relatively poor time and frequency resolution. However, what we have to do is we search these data streams in real time, 36 from all 36 beams, and when we detect a burst, we can trigger a voltage buffer. So the voltage buffers are 3.1 seconds in length, so everything has to happen pretty quick here. But these voltage buffers are the things that allow us to really understand the burst at this point. So we can use these voltages, of course, to correlate them and then make an image of the burst and pinpoint the locations. We can also use them to study the burst in high time resolution. So what we can do is we can, in fact, get down to 3 nanoseconds time resolution now. The burst will also deliver us polarization. So we can look for rotation measures and study the intrinsic polarization properties of FRBs. Because of the way the search works, it's an incoherent sum search. We get a signal-to-noise ratio improvement when we go and look at these voltage buffers as well. So we get one bit from the fact that we can add up from the square root of the number of antennas, so that's going to be on the order of 5 to 6. And then we also get advantage because we don't have to. We're not stuck with this relatively coarse time and frequency resolution as well. So you'll see that if a detection's on the order of 15 to 20 in the search, it can go up to over 200. So we can look at these bursts in very exquisite detail. So in general, how this works is we image the burst. We look for radio continuum sources in the field. Right now, the model is to go and look at those same sources with the compact array at an interferometer in Australia, or the VLA. That gets referenced to a reference frame, which we can relate to the optical reference frame and then into our optical images of the field to figure out where identify host galaxies and where within host galaxies these bursts are coming from. And this can deliver us positions as good as around 100 milliarc seconds. So once you have your position, you can follow it up. You do imaging and sort of long slit spectroscopy with all your favorite 8-meter class optical telescopes. You can use your favorite radio interferometer to do the astrometry and to search for persistent radio sources. Your favorite 100-meter class single dish telescope to search for repetitions. Your favorite space or millimeter interferometers to look for high spatial resolution studies of the host galaxies. And your favorite integral field units to study, again, the kinematics and gas content of these host galaxies. So this works most of the time. And this is where we're at. So we've localized 9 FRBs now. I've arranged things here from low redshift to high redshift. So you can see here, we'll go into more detail of these in a bit. But you can see here, this is in a spiral arm of a galaxy. You can see examples of where things aren't lining up correctly, and I'll discuss that in a bit. But in general, you can see we've detected things from redshifts of 0.1 up to redshifts of 0.5. You can also see that we've measured rotation measures, and the rotation measures on the vary from the order of like around 10 down here to 360 up here. So yeah, I said there's 9 localizations. I'm going to call it 6.5 plus or minus 0.5 redshifts. We've got we've detected 2 FRBs in our commensal mode, and all the FRBs have been at high latitude, so we're not having to deal with the Milky Way as much. Dispersion measures are between 290 and 550. As I said, the rotation measures are between 10 and 360, and a lot of them are in the orders of tens. I just plotted you a couple examples here of what polarization position angle looks like for a couple of high rotation measure FRBs, because it's nice to see that lambda squared signature. So I just want to point a few examples about life's not easy. You don't get handed a L-star galaxy all the time, and for this FRB here, this is going to be tough to see. It's offset from this galaxy here, so there's a question as to whether or not the FRB is coming from here or something else. And really, to figure out to make a convincing argument about where the FRB is coming from, we really need to line a slit up here and hope to see emission lines coming from the FRB position. But we're confident that that's actually the radio position of the FRB. So I guess just to revise things a bit, well, I guess, going back to 1809-24, well, at first it was unclear whether or not this was a sort of lenticular galaxy or an early type spiral galaxy. We think it is actually early type spiral now, so we argue that there is star formation. And when you go and look at the galaxies versus their galaxy mass versus star formation rate, the majority now are up on the the blue sequence here, so they all are showing some evidence or some star formation for the most part. From the first 4, we were coincident with massive galaxies, so the chance of that happening is exceedingly small. As I said, most show evidence for star formation. The ones where we have high precision, they seem to be offset from galaxy centers, so we argue that they're not associated with AGN in many cases. I think a similar argument about the associations with the L-star galaxies rules out them being in satellites, because you'd expect some of them to be sort of way off the galaxies, but we can discuss that more. We haven't seen any evidence for persistent radio sources, despite even having galaxies at 0.1. So you're left with FRBs originating in a diversity of galaxies, and at that point you'd argue that pinning down the progenitors is going to require higher angular resolution and burst astrometry and comparable resolution at other wavelengths. Or how is there more than one formation channel? And this plot here is just showing you sort of the galaxy types which you'd expect to see superlunar supernova in, and double neutron star type things, which is sort of 2 channels to produce magnetars. But it's a diverse. The galaxies at this point are very diverse. However, things got a bit more complicated a few days ago. So X did some preliminary work on this host galaxy, and it's sort of down here in elliptical galaxy land now. So, the story evolves with time. So this meeting is about more about what causes FRBs than what we can do with them. But this is again the next plot from this morning, and here's dispersion measured redshift. And first of all, it's real, right? This is we've been trying to do this for we've been saying this for a while now, but you can see that we can now actually use the FRBs themselves to make a local estimate of the local baryon density, and it's consistent with the early universe measurements. And we would argue now that this is a far better method than using other sort of optical approaches to studying or other approaches to studying the local baryon content. And so the next step here would be to use to understand the scatter in that relation and use that to sort of study feedback. The process of how AGNs affect the IGM and CGM. So for the last little bit of the talk, I just want to tell you about what we can do with FRBs in high time resolution. So we can take our voltages and do a few things with it. So we can either form a tight array beam, or we can just do high time resolution imaging. And either way, we can get much better than 1 millisecond time resolution. So here's 180924. This is what it looked like in the incoherent sum, but when we do the high time resolution imaging, this is what it looks like. And so this sharp rise time and exponential tail, that is, again, what scattering is. That's scattering from a thin screen. There's no evidence for foreground galaxies, so the scattering here is likely from the host. But the key point here now is that this burst is very intrinsically narrow. We'd argue it's less than 40 microseconds. So when we're thinking about FRBs, for this one here, you need to have 4 times 10 to the 34 ergs per cubic centimeter of radio photons within the ASKAP band to produce this burst. So it's something that we need to think about, but bursts can be very narrow. Again, Vicky mentioned this burst, which was interesting because it was coming from this galaxy. This is in the foreground, and what we were able to do is investigate the properties of the halo galaxy from the burst's rotation measure and scattering properties, and put in really complementary studies of how bursts, complementary studies of halo gas compared to what people could do, in optical. So when you zoom in on this burst, some of this is going to require you to squint at screens and stuff like this, but there's obviously 2 components here, but these 2 are also significant. You have to trust me on this one, and maybe I can show you it on my computer screen later on. But so this is work being led by Hiran Cho, very talented undergraduate student who's been working with us. The 4th component shows up. It's very obvious in Stokes V. The second one is it's kind of there, but these are very faint pulses. But I've tried to show you a few waterfall plots to try to convince you that these things are significant. If you can look down here, this is it here. It's got a bit of a different dispersion measure than the other pulses. These 2 pulses here, you can measure the rotation measures, and the rotation measures are different. So when we look at the polarization of it, the first thing to note here is that the polarization position angle of this pulse here over a few hundred microseconds is changing. The polarization position angle between the 2 pulses is different as well. And in general, the polarization properties of the pulses are different. Yeah, so as I mentioned, the pulse has a different apparent dispersion measure, stronger in Stokes V, and this one has a different rotation measure. So it's obviously, one obvious explanation would be for the object to be rotating. I think the other possibility is that there's propagation through a relative plasma, either within or surrounding the magnetosphere of whatever's producing this thing. And again, another point is that we often see apparent rotation measure variations in pulsar profiles or magnetar pulse profiles as well. I think one attractive thing would have been to explain these pulses as being to do with a propagation effect in the foreground galaxy, but given the differences in the polarization properties and shapes of these pulses, is a bit that's a bit more tenuous. But going forward, I think these FRBs are going to be very useful for studying that as well. So the second example is this one. Again, this is the most nearby FRB. It was it's in a Sloan galaxy. It's got this very high rotation measure. So this, and given that it sort of sits above the DMZ relation, this sort of implicates potentially a host galaxy contribution by the fact that there is also this high rotation measure as well. But this is where it comes from. So this is HST observations of the field, and you can see here this is in UV, and you can see here it sort of sits on a spiral arm of this galaxy. So yeah, it's a very scattered pulse profile. So it suggests that we're able to use that to study what's going on in the sort of intervening IGM. So in the last 30 seconds, I'll just show you a couple of other examples of FRBs in this high time resolution mode. So this is the one that was shown that's kind of offset from the host galaxy, but it's got evidence for sort of scintillation here. Scintillation is not coming from our galaxy, but coming from somewhere else. It's got 2 pulse profiles, and again, if there was a bit higher sort of fidelity in this waterfall plot, you would see that this plot looks like it's kind of doing the typical sweepy thing on the second pulse there. here's now finally an FRB that we haven't seen repeat, but shows again what we see from many of the repeater pulses. So it's a very wide pulse profile, and shows the whatever sad trombone thing. So we'd expect this one to repeat as well. So the next steps, we want to collect a larger sample of bursts. I'm not quite sure what our event rate is right now. It seems a bit non-Poissonian, but we're working on that. Going forward, we want to upgrade our system so that we are not doing this incoherent sum, but we're doing a coherent search, and that will increase our event rate, but it requires a lot of GPUs. But before I wrap up, there's a few other things that we could talk about. This one here was detected as an image plane transient as well. So that's what it looks like in the image plane in a 10-second 10-second image. This FRB here was 2 arc minutes from Fomalhaut, and also we've detected repetitions from this pulsar, but that's published. So I'll just conclude here. We got a DM redshift relation. FRBs come from a diversity of host galaxies and have a diversity of pulse phenomenology. But really, we can use localization, high-time resolution studies to really understand FRB emission and FRB propagation effects. Thank you.